Okay, let's talk about the most common flavors in ecohydraulics um, of these habitat suitability curve models, these habitat suitability models. And these are PHABSIM and IFIM. Actually, yeah, I'll come back to IFIM. So the PHABSIM stands for Physical Habitat Simulation Software. Here's an old hard copy scan of this. You can go to that link and get it. So published in 1978, right? So hydraulic simulation and in-stream flow studies. And so the techniques that we were just describing, these were developed in the 1970s. This is to date still the most widely used ecohydraulic model. There is confusion because in the late 70s, early 80s, and through the 90s, the vast majority of PHABSIM simulations were all run with 1D hydraulic models. Why? Just like we talked about in the hydraulics, that was the only thing that we really had the computational power to do, right? 2D was, something that could theoretically be solved, but the computing power wasn't there. And in practice, also, our topographic surveying techniques weren't good enough to get that good of data, right? And so oftentimes people will kind of, kind of discredit PHABSIM a little bit and say, oh well, yeah, and equate it to just the 1D applications of this. But do know that it's still not the software program, but the technique is still in broad use today. Okay. So now there was, this was a big deal that by 2001, right? It went from a DOS program that was run at a command prompt into a Windows program, right? And there was a graphical user interface for using these things. It was a big deal. But this was how you discretized space. This was how you represented it, right? You took cross sections, and at each cross section, right, these right here, we might have thought of when we were talking about 1D hydraulic models, we might have thought of those as the different roughness. In this case, they might represent different cover classes, different substrate classes, etc. And each cell in the cross section would have a depth and a velocity solution, and we would be interpolating in space in between, assuming that what's calculated at this cross section versus the cross section upstream at it, that if we average in between those, that's what's representing what's happening in those cells in between. So that was how things were discretized in space, and that was largely, like I said, to a function of what I could do with an old level, right? And how we could collect data, as well as the computational limitations of the past. So the hydraulic model, right? If you were to download this DOS version, right, you can create a new project, and the hydraulic model that was used in these original versions were these one-dimensional, right, water surface profile models. Use the step backwater method. So this is solving for energy. We didn't go through that derivation here, but we did talk a little bit about it. And it's a one-dimensional representation of the flow. So that's how these things worked. Then what they would do in that discretization of space in between those cross sections, they would assign those cells, if you want, if you will, each one of these areas, like this one, they would assign that a composite index value, where they would be basically calculating what they could at the cross sections, and then averaging in between to get this composite value of what is a representation of habitat quality in between. Okay. Now, it's interesting because while there was a very low degree of, let's say, sophistication in the hydraulic model representation, right? Just these one-dimensional instead of 2D or 3D models, and the topographic representation of space, One of the things that they actually did a really good job on in these models was a reasonable representation through weighted usable areas of the temporal considerations. And a lot of this was based too on the driving problem. If the driving problem was FERC, Federal Energy Regulatory Commission, relicensing hydropower dams and trying to figure out how flow operations would impact fish, what they would do is come up with a weighted usable area. So if we just focus here on this blue, okay, this is for fry, okay, so life stage of fish. And so these, fry just emerging from the gravels, what it's basically showing is that there's a lot of weighted usable area at very low discharge, right? And then it drops really quickly as you get into higher discharge. So right here, this is 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 actual hydraulic model simulations, which are steady state simulations at different discharges, okay? And then those hydraulics were used to drive one of these habitat suitability curve models. And all weighted usable area does is say, okay, well, if I've got some sort of composite, suitability for, one of my cells, those spatial cells that we were looking at, right? What's its overall, if I kind of sum up all of those and say like, okay, well, of a one particular quality, how much area do I have, of this? And so this weighted usable area, notice here, this is, square feet per, 1,000 foot of river, okay? So you would choose some threshold typically above which you're going to consider it suitable. So on a 0 to 1 scale, I don't know, maybe that's everywhere that it's greater than, it would depend on the method you use to combine these things. Maybe it's, if it was average, maybe it's something high, like everything greater than 75%, 0.75. If it was a product, maybe you'd use something lower, like everything greater than a 0.4. But you would choose a threshold, and then you'd be literally calculating how much area is there above that, and then you would sort of you would normalize that based off of these based off of some sort of linear, distance in this case, right? So square feet per 1,000 feet of channel. So what that allowed you to do is then you do that to get each dot, and then you could run different ecohydraulic models for these different colors. These are different life stages. So that would have been fry, then the juvenile, then the adult, and then this would have been spawning. And so this is the information that would go into informing how flow releases are going to impact. So when are fish fry? When are fish juveniles? When are they adults? When are they spawning? Different times of years. And then these would be used to set operational limitations on how the dams came up with their hydropower release schedules. That got formalized into what was called the in-stream flow incremental methodology. And this came out of USGS and Fort Collins. And so here are different life stages, okay? And they're saying, well, juveniles need habitat all the time, right? The adults tend to just be in here, leading right up to, when they spawn. And then there's this, incubation period in the eggs for this particular, steelhead trout species. And so what they would do is they would look at, well, what's a natural hydrograph, right? And they would break that into functional groups, right? One's our adult, spawning, incubation, juvenile happening. And then they would look at, well, what are the actual flow operations during those periods, and at what point are we running flows too high, and at what point are we not running flows enough, and see if they can make adjustments to how how the flow releases and how the dam is operated. And the whole idea, this is a very common sort of engineering approach to solving, to problem solving. The whole idea is this idea of optimization. So it's, ask what the fish need. Ask the fisheries biologist what the fish need. What do? They go out and observe what the fish are using and then come up with these empirical curves and then run a model and then say, right, well, this is what the quality of habitat is at this flow. This is what the quality of habitat is at this higher flow, et cetera, et cetera. And so they would basically use this to assume that the habitat is basically, the topography is basically fixed, but what you could change, what you could control the knob on is the flow. And if you can change the timing of flow to align with when the needs of fish are, you ought to be able to optimize, okay? And that's basically what, gave birth to a discipline called ecohydraulics. PHABSIM, a simple ecohydraulic model, and then IFIM, a methodology for attempting to try and put these pieces together, typically for a single species, but occasionally for a couple of species, or maybe, if they got really fancy, a handful of species, and see what you could do to optimize, where you're going to cause the least harm and provide the most weightable usable area. That's the game.